Yeah.
Thank you.
Okay. So, yeah, good morning, good afternoon, and good evening, everyone. Thanks to organizing committee to invite me to chair this meeting, as Professor Bell couldn't attend this meeting today. So today we are very pleased to invite Professor André Timmins from the University of Houston to talk about the LHC. André will discuss the proposed physics program, new detector concept, and expected physics performance of the LHC. So this title of the talk is LHC, a new horizon for QCD. Before André's talk, I would like to briefly introduce André himself. So André received his PhD in 2008 at the University of Birmingham. The research field was in experimental nuclear physics. Then he was as a postdoctoral researcher from the 2008 to 10 to work at the Wayne State University. And then as a visiting assistant professor from the 2010 to 12 to work at the University of the Houston. And then as an assistant professor from the 2012 to 18 at the University of the Houston. From 2018 until now, André is as an associate professor to work at the University of the Houston. So André has been also RHIC staff member since 2005 and has been Alice member since 2010 and Eric member since 2021. André has made a very important contribution on characterization of the initial state, medium properties, and collectivity in heavy ion collisions. Regarding to the leadership roles, he is the coordinator of the LHC-USA collaboration from the 2022, and also a co-chair of the LHC review paper from the 2021. He is a topical convener of the QGP evaluation and its dynamics properties section for LHC review paper. And also is the correlation and fluctuation physics working group convener for LHC collaboration from the 2016 to 19. And I was also the flow analysis group coordinator for LHC collaboration from 2013 to 16. And also the light flavor spectral physical working group convener for star coloration from the line 2009 to 11. So thanks so much. So now let's come to André talks. André, could you please share your screen and start your talk now?
Yes, everybody can see the screen. Is that right?
Yes, I think that's right.
Okay, very good. So thank you for the introduction and being willing to chair at the last minute. Thank you, and of course thank you to the organisers of this seminar. And I've heard very good things about this seminar, and I've tried to attend as many talks as possible, and they've always been excellent. So I just want to thank the people behind this for that endeavour. So the talk today will be on Alice Free. My name's Anthony Timmins, as the chair announced, and the vast majority of what you see is going to be based on a letter of intent that we submitted at the end of last year, and I put the arXiv link on the bottom left here, and yeah, I will start. So. Just to begin with, with some essential and important features of QCD. So here I list 3 hallmarks. One is asymptotic freedom, and it's this idea that the strong force itself will vanish at high energy, which is manifested by the coupling constant decreasing. The second is confinement. That's the fact we can never separate quarks. What we have in the middle is a famous lattice calculation of heavy quark, anti-quark pair, and once he's at a particular distance, the potential starts increasing with distance itself. And then I think the third salient feature is chiral symmetry breaking. This is the main mechanism to generate mass in the universe. It's responsible for about 95% and actually generates way more mass than the Higgs boson. It's one of the facts sometimes I share with my high energy colleagues at the LHC. And these are extremely important. I mean, the asymptotic freedom and chiral symmetry breaking is both garnered Nobel Prizes. Let's see what the next Nobel Prize in QCD will be. I'm sure there will be one. So QCD itself, it's extremely interesting, but I think very challenging. One can write a Lagrangian, which is essentially contributions from quarks and gluons to the QCD field, but it's actually, and this may be the full representation of the truth, but it's actually extremely hard to unlock this and try to use it to predict various things. But we have. So in the high energy limit, one can approximate this using perturbative QCD, and one can try and predict the running of the strong coupling constant or cross sections for various hard processes. In the low energy limit, and I define energy in terms of how the energy of the interaction compares to lambda QCD, which is 200 MeV. In this limit, we can partially solve it. So what I showed before was a extremely important example of that, this potential. So we can use it to determine those potentials, the mass of hadrons, and a few more things. But when it comes to low energy processes that evolve with time and space, the Lagrangian then becomes untractable, very, very difficult, if not impossible, to solve now. This in particular can relate to the space-time structure of hadrons or nuclear structure and hadron formation processes, and so on and so forth. So this is the situation we're in. Some people love testing QCD, where you can test the theory directly in terms of perturbative QCD and lattice QCD. Others like to explore behavior where the theory doesn't give us any guidance, but at least where we have experiments, we can collide things and map this region in a very sort of experimentally-led way. And we often use phenomenological models to help us understand things, in particular the string models. So one of the key predictions from lattice QCD that excites many, if not all of us in this meeting is the emergence of the QGP. So lattice QCD, I mean, what I showed you before for the potential, this was calculated at 0 temperature, but you can run lattice QCD at finite temperature. And if you do so, it predicts a rapid change in the thermodynamic properties for QCD, or around 150 MeV. We believe this is an indication of the formation of the quark-gluon plasma. It's certainly an indication of a change of state when thermodynamic variables start changing very quickly around a particular temperature. And if the system has as much antimatter as matter, it's symmetric in that way, then we think we have a crossover transition, so a second order transition where one sees a rapid increase in these variables, but no discontinuity. And lattice QCD, as well as predicting these thermodynamic properties, usually there's an order parameter associated with the restoration of chiral symmetry. So this generation of mass essentially receives in the presence of QGP. So how do we create a QGP? Well, as many of us know, we utilize heavy ion collisions to do so, and perhaps proton lead and PP. And this is just a demonstration of what, and I'll put it in inverted commas, our standard model of heavy ion collisions. You first start out with two nuclei that are extremely Lorentz contracted. When they collide, the system is highly out of equilibrium. You can see these very hot spots and these very cold spots. And then at some point, these hot and cold spots smooth out, and the system then exhibits a hydrodynamic expansion. It will then cool down while it's in this QGP state and then reform hadrons. These are emitted at hadronization. They can rescatter, and then eventually what we get right at the end is the frozen out hadrons that we measure in our detector. So as many as you know, these are the machines that have the most collaborators, I would say, or the most popular machines that we all work on that collide heavy ions. We've got the relativistic heavy ion collider at Brookhaven National Lab, and the Large Hadron Collider at CERN in Geneva, Switzerland. So there's huge value in colliding heavy ion collisions at different energies, I would say, as many people that attend this seminar will be well aware. The focus, of course, in this presentation will be for the highest energy collisions, which corresponds to this part of the phase diagram, which is the most antimatter symmetric QGP you can make, and it's also the highest temperature QGP you can make at the LHC. Of course, there's an ongoing dedicated high energy program at RHIC. We have STAR, of course, and then the new S-Phoenix detector, which has begun taking data. And there are other programs at SPS in terms of lower energy. And of course, we've got the RHIC Beam Energy Scan, where essentially one is trying to look for evidence of a QCD critical point. That's when this second order phase transition would become first. And of course, one actually also wants to look at the thresholds for QGP formations at lower energies, because that usually corresponds with lower temperatures. So I just want to sort of go through briefly what I feel the major discoveries were over the last 20 years, just to try and set the context for what we need to do over the next 20 years. So it's going to be, I think these slides certainly more sort of RHIC and LHC focused compared to SPS and lower energies. So forgive me if I miss anything. But of course, around the early mid 2000s, we discovered two extremely important things, and that one was the hydrodynamic description of flow measurements at the top RHIC energy. And of course, we discovered for the first time the suppression of high momentum hadrons at RHIC, which we have extremely compelling evidence that this is due to partonic energy loss in the QGP. And then I have a link to one of the famous articles that Brookhaven written around the time, where it stated that the scientists served up the perfect fluid. And these are really major discoveries, which I think really changed the paradigm in terms of how we understand a QGP, how it evolves, and frankly gave extremely compelling evidence that we really do make a QGP. So the LHC turned on towards the end of the 2000s and the start of the 2010s. And I think it had its own set of discoveries. And of course, I will say that this is also an era where RHIC kept running and started to garner huge statistics, in particular the STAR experiment, with the many improvements in how the TPC worked and so on and so forth. So with the LHC, we started to see that perhaps small systems, if you select proton-proton or proton-lead collisions with that produce lots of particles, they start to exist QGP type behavior. So I have a plot from Alice here, which shows strangeness enhancement, but this was also seen at RHIC by the Phoenix collaboration and indeed the STAR collaboration later on in terms of the hydrodynamic description of flow. I also think we learned a tremendous amount about charm in the last decade or so. We certainly established the fact that it indeed flows. These are V2 measurements. This was done both by the LHC and RHIC in this sort of higher statistics area, which really shows it couples with the QGP medium. And of course, I have to advertise the Alice review paper, which of course goes through the Alice specific things, but since that's been asked before, I was a co-chair of this. I never lose the opportunity to advertise it, and we try to look back at the last 10 years, essentially from an Alice perspective in terms of these discoveries. There are other QGP related things. I mean, these things I think are a bit more specific to the LHC, and that's particularly the Charmonian studies. This is the suppression factor for J size, and you see at lower energies, one sees an increasing suppression as the system gets bigger, but then we have this funny effect at higher energies where actually the suppression recedes in very central lead-lead collisions. This was one of the original signatures that was expected just to be suppressed by the fact that the potential is compromised in the QGP between the quarkonium, so you get some melting. But it turns out we produce so many charm quarks at LHC energies that indeed can happen, but then the charms quarks can then recombine to form the J site again, leading this to this regeneration effect, which we also believe is actually, despite the fact it was a surprise, is also evidence of deconfinement. And I think also something that the LHC can do quite well is not only full jet reconstruction, but it can do it over the widest kinematics because it has the largest energy jets available, essentially. And now there are some real serious attempts to ask how can we use jets to probe the microscopic structure of the QGP at various scales. I should also mention I'd say the non-QGP studies, which got a lot of attention for very good reason. I think Laura Fabietti presented one a couple of weeks ago. So these are PP measurements. So recently in Alice, we confirmed this dead cone effect, and that's the fact that if you have a charm jet relative to a light jet, you have a suppression in radiation in the direction of the jet. Femtoscopy has taken on a whole new life, I would say, and this is exactly what Lara presented a couple of weeks ago. I think it was more the latest studies, but we're now using femtoscopy to look at interactions between readily produced hadrons. In particular, here we look at the proton-hyperon interaction. We find it's attractive, and these things actually start to have implications for things like the neutron-star equation of state. And it's also another way to test QCD, which I think is really quite cool. And we're also starting to see some peculiar things in terms of hadronization. So we found that hadronization, it's not universal in a clean system, in the sense when you have a proton-proton collisions, you have far more charm baryons relative to charm mesons compared to the case in E plus E minus collisions. So this mystery of hadronization is something that we cannot predict from first principles, is still throwing up some surprises, and we obviously would love to understand why. So that's my sort of overview slide, so to speak, and now I'm going to be sort of a little specific about the machinery of the Alice detector and what we want to do to upgrade it. So it's the only detector at the LHC that's specifically designed for heavy ion physics. Of course, the other detectors can have many fantastic heavy ion measurements, no doubt about that. It has a broad momentum acceptance, and it really has a world-leading particle identification capabilities. Every single one of these measurements relies on very good PID, and these were all done by the LHC detector in the 2010s. So we've just began run 3, so we can start looking ahead to what we might do in the later years at the LHC. What I have here is
excuse me. Sorry.
Oh, yes.
Sorry, Anthony. Just the technical issue is we always see the title. Your title page appears every time you change your slides. Your title page appears again. Is something wrong, or you do it on purpose?
No. I think you've seen the title once. Should I switch to Keynote to see if that works a little better? Yeah. Or
if you have Keynote, maybe can you try to just share?
Yes,
the Keynote?
of course.
Yes,
just let me stop sharing.
Yeah, sorry
my
for.
apologies. Yeah, let me try because we know. Yeah, I'll share the screen. Oh, yeah. Okay, can you see the screen?
Yes, but not yet in full screen mode. Yeah, now I see. Yeah, thank you. Yeah.
And is it switching to the title when I switch the slides?
Can you try to go to the next slide again? Yeah. No, I think now it works better.
Okay,
yeah,
okay.
Yeah, thank you. Sorry for interrupting.
No worries. Thank you for telling me. It's hard to see when you're on this side. Yeah, so I was coming to the LHC schedule. So we're in the midst of run 3. We are taking a long heavy ion run this year, which should be followed by a PP run next year, and then an oxygen run, we hope, at the end of run 3. And then we have a shutdown for upgrades. Run 4 will happen, where we'll do PP, P-lead, and lead. And then we have run 5 and 6, which I'm certainly going to talk about in much more detail in this presentation. What I have on the right here is the luminosities provided by the integrated luminosities provided by the LHC in terms of the run number. And you can really see this sort of really impressive increase in performance. What we have in the blue is PP. What we have in the yellow is AA, but it's the nucleon luminosity, not the heavy ion luminosity. But it's interesting that even in 1 month of heavy ion data, by runs 3 and 5, we're going to get as many nucleon collisions as one gets proton collisions in 8 months of taking, which I think is pretty cool. So Alice itself, it's going through some major upgrades in the 2020s. I think perhaps the biggest upgrade is our TPC now runs in continuous readout mode, which means it can collect about 100 times more data in a given time period compared to how it was running before. And I show on the right just the energy loss versus momentum of the TPC running in PP, and we see this beautiful separation of peaks, and there's every indication that the performance in terms of track quality and DDX is similar to what we had before, but in the context of way more data. We also have a new inner tracking system, the ITS2, and then we have a muon forward telescope for run 3 as well. And then in run 4, we are going to put a calorimeter very far forward, and then improve our inner tracking technology even more with the introduction of run 3. In terms of the physics goals, I've been quite brief, but I would say this will hopefully open up a more precise area for jet, heavy flavor, and electromagnetic probes in both small and large systems. And We will also be able to perhaps explore much more deeply the proton and nuclear structure and look at very sort of rare hadron interactions with this new setup. So then that takes us to what happens after run 4s, which is going to be run 5 and 6. And this is where we propose to essentially build a completely new detector. And this is what we refer to as Alice-free. So we will not use gas anymore. We're going to go with all silicon for the main tracking. So we'll have an all silicon tracker with a high resolution vertex detector and extremely low material budget. I will go into details of that in the next few slides. This is going to be placed within a superconducting magnet system that can give us a field up to 2 Tesla. We will still maintain our tradition of world-leading particle identification. So this will be possible over a large acceptance for muons, electrons, hadrons, photons, and actually more particles than they state here. And by large acceptance, I mean eta will go up to around 4 compared to around 1 for our main tracking detector. And it will also be very fast. So we'll have a fast readout and online processing. Yeah, as I mentioned before, it hopes to start taking data in 2035. Here I have a schematic on the right. As I say, I'll go through these in a little bit more details, but we have our sort of main tracking detectors are in the yellow. The RHIC detector is on the outside. Our top detectors are sandwiched between various layers in the main tracking detector, surrounded by a superconducting magnet, and then the muon absorbers and the muon chambers to detect muons are on the outside, and then the MCAB will fit in here. What's actually quite interesting is we have to place it within the original magnet, so to speak, because I believe the original wall magnet that we had, the big red thing that you probably see on the back of my screen, is a little bit difficult to move, but that's okay. We'll just place it within it. And I think there's actually something you gain by not removing the wall magnet. I can't quite remember what. Okay, so I will just start off with some general features of the performance, if you like. So what I have on the left are the expected luminosities, both per month and for the entire duration of runs 5 and 6 for top energy PP, the PP reference, which is the same energy as heavy ions. And then 2 projected integrated luminosities depending on the particle species. This is for xenon-xenon, and this is for lead-lead. We'll be able to collect all the luminosity that the LHC gives us for heavy ions, so that correspond to hundreds of billions of heavy ion events. What I show in the middle is the evolution of the pointing resolution with respect to time. So the pointing resolution is our resolution at the collision center in terms of distance, and this is very important when it comes to separating decay particles from prompt particles, which you'll see later. So you can see how this resolution is going to improve as Alice evolves, and what we have on the x-axis is essentially the interaction rate times by the acceptance, so the amount of data we're taking per second. And again, as we go forward in time, we see order of magnitude improvements, both in the amount of data that we can take and the quality of the data, I would say, in terms of these pointing resolutions. So the detector itself, I mentioned it's going to have a much larger eta range. We're still going to be able to reconstruct down to very low PT, so the resolution is roughly 1 to 2%. Going from 0.1 to 100 GeV, and then on the right we have some efficiency curves for various hadron species. So how is this all achieved? So I'm going to go through some of the main subcomponents one by one. So I mentioned this pointing resolution before. It will have it will be of the order of a few micrometers around 1 GeV. And how do we achieve that? So I have this nice equation that we have in the Alice review paper, which shows that this resolution is proportional to the distance away the first point on a track is away from the beam, times by the square root of the relative radiation length. And there are some kinematic variables here that this will depend on too, in particular ET and 1 over PT. So in order to get the best pointing resolution, you have to basically put the first point you use in your track as close to the beam as possible. And we achieve this by having this retractable vertex detector that can get all the way to 0.5 centimeter away from the beam. It is retractable because at injection energy, the beam is much wider compared to at full energy. So when the beam is being injected, you want to retract this outwards, and then at full energy, then you sort of want to retract it inwards, so to speak. This is actually something that's also being pursued by LHCb right at this moment. They have a similar device called the Velo detector. So we're looking very carefully how it works for them and so on and so forth. But there's more than one point in the vertex detector. There's actually 3 tracking layers, and here you see the distances of 2 of the tracking layers away from the beam for when the thing is closed and when it's open. It will also have extremely small radiation length. So the radiation length is basically how far a particle travels on average before it interacts with the detector. This is also something that's essential when one looks at this equation. The technology itself will be based on silicon pixels, so to speak, which are going to curve around, be very thin. That's how one achieves these very low radiation lengths. And because they're very thin, they also need very low power and very low infrastructure, which also reduces the radiation lengths. And each point will have an intrinsic resolution of 1.5 micrometers. So that's essentially our proposal for the inner tracking, so to speak. And then, of course, beyond the vertex detector, which is this thing in color, we will have an outer tracker that will correspond to roughly 60 square meters. And again, this will be silicon pixel. It will have 8 barrel layers for mid-rapidity. And these barrel layers measure tracks that come in this direction. And then for the forward rapidities, what you have to do is you then have to change to a disk structure. So we actually have nine disks in order to make measurements at larger rapidities. These are the dimensions. So R out is essentially this distance. It's the circumference of the circle in the cylinder, so to speak. And then RZ is half of the length of the cylinder. I've got a few more dimensions here, the pixel size and the pixel resolution. And again, we'll have quite low radiation lengths for this, for the outer tracker, around 1%. And I'd also say that both of these technologies, the inner and outer tracker, will build on the experience that we have with the ITS2, which is what's running at the moment, and then ITS3, which is going to be our new inner tracking system in Run 4. Essentially, you can probably think of the vertex detector being very similar to ITS3, and you can think of the outer tracker being very similar to ITS2. In terms of particle identification, so we don't have gas anymore. So what we do is we're actually going to have 2 TOFs, an inner TOF, which is about a radius of 20 centimeters. So roughly in this direction, in that place, and then an outer TOF at 85 centimeters. And then outside of that, we'll have a rich detector, which detects Cherenkov radiation. And then one can, of course, use all these 3 detectors to do a combined PID. These are the central detectors at mid rapidity, but we're also going to have NCAF CAF-enriched detectors to get the full coverage. And these are our specifications at the moment. What we hope to have is a time resolution of less than 20 picoseconds for the TOF, and then an angular resolution for the Cherenkov detector of less than 1.5 milliradians. What I list here, and I won't go through them all, is essentially the full ALICE-free detector requirements. So you can see that we will also have muon detection capabilities, which I mentioned before, and electromagnetic and MCAL, which is particularly useful for high PT photons and electrons. And then we also plan to put a very forward conversion tracker to detect soft photons, which I'm going to talk a bit more about later in this presentation. Okay, so in terms of planning, so the letter of intent that we have written, it's already been reviewed by the LHC committee, which is essentially the authority in terms of if you want to put a new detector or a new sub-detector, one has to get approval from them, and it got very strong support. Right now, we're in the process of selecting technologies, looking at small-scale proof of concepts, and then also trying to figure out which country is going to do what within ALICE in terms of ALICE-free. And then the next few years, we would then plan on large-scale engineering prototypes. There will be technical design reports, which also have to be approved by the LCCC. And then at the end of the decade, we'd start constructing and testing. We give ourselves a year for contingency in case something is slowed down for whatever reason. Then in 33 to 34, we would prepare the cabin for the new detector and install it. And then 2035 to 41 will be when the Run 5 and 6 ALICE-free physics campaign will begin. So, of course, the next question is, what sort of physics do you want to do with ALICE-free? And I try to sort of boil this down to quite generic questions. I hope that's okay. And of course, these are some of the questions I have. You know, what more can we learn about the QGP? Or can we learn more about the QGP? Have we exhausted our tests of fundamental QCD? Is there a way that we can explore? Is there more we can explore regarding hadronization and hadronic interactions? And can we contribute to beyond standard model searches more than we have? And I think, of course, the answer to the first question is yes, the second no, and then yes and yes. And in terms of hadronization, I do have an example of an omega CC. So this is an omega with two charm quarks and one strange quark. And essentially our ability to reconstruct it. I'll go into these types of multi-charmed hadrons, hyperons in more detail, but this is one of the performance plots you can find in the letter of intent. So, you know, sort of focusing on the QGP related studies first. As many of us know, the vast majority of QGP temperatures estimates, they come from models which are constrained by data. And obviously, I think that's fine to a degree. So what we have here is a plot in the ALICE review paper, which the top thing shows the order of the temperatures that are evolved, so to speak, in a typical hydrodynamic model that will describe many observables. One can also compare the starting temperature one needs to describe the suppression of the relative suppression of the upsilon states, and there's a range of temperatures that corresponds to different models here. One can measure temperatures a little bit more directly without this model data coupling, so to speak, by measuring direct photons. So I quote the temperatures we have at the moment. One can get an effective temperature from hadrons. This is something that Olitro and co tried to determine in one of their Nature papers. And of course, we can use thermal models or blast wave models to determine the chemical freeze out and kinetic freeze out temperatures. And what I indicate here is the lattice QCD crossover phase transition range. So most of these come from, as I say, this data model coupling, so to speak. I think traditionally, you know, when I measure the temperature of this room, I don't really need a model to do it. I actually have a thermometer that can do it in a model independent way. And as I said before, of course, we have photons that is perhaps the most direct probe from data, but these have the issue that the blue shifted because the QGP is expanding. Now, it's believed that the dielectrons, perhaps the best way to probe the QGP temperatures directly, because one takes the invariant mass spectra of 2 electrons, and this, because one looks at a mass, is by definition Lorentz invariant. So in principle, one can get temperatures directly from the dielectron mass spectra, and this is something that Frank spoke about in quite some detail a few weeks ago. The challenge at the LHC is this is very experimentally difficult, because these electrons have not only contributions from the QGP, but from heavy flavor decays such as CC bar and BB bar. And one can measure this in the blue and then determine the contribution from decays. And when this is subtracted, you really don't have so much left, at least in the high mass region, intermediate mass region, which one uses to try and get the temperature itself. So because of these excellent pointing resolutions that I mentioned before, ALICE-3 is really able to separate quite cleanly the electrons that come from the QGP directly, which we refer to as the prompt electrons, and the decay electrons from CC bar pairs, which are weak decays and happen after the QGP is formed. What we have here is the DCA of the electron pair for prompt electrons versus decay electrons. And one can see quite a clean separation in these peaks. So in principle, what one can then do is then put a cut of around here, and then you'd be really dominated by prompt electrons. So that's the capabilities we have, and we think we can get an extremely clean electron signal as a result of this. And what we have in the middle is one of our performance plots, so to speak, where all these things are subtracted, and what's left is the statistical uncertainties. And you can see these, number one, you have a very, very clear signal, and number two, these uncertainties are extremely small. And essentially, to get the temperature, what one does is one fits an exponential to this part of the mass spectrum, and what one gets the temperature direct. Now, a measurement of this will certainly be possible in run 4 and 5, a good measurement with the ITS-3 detector. But what ALICE-3 can actually bring is this idea is if you start increasing the PT of the electrons that are emitted, you start to get sensitive to higher temperatures and therefore earlier times. And what we have here is a projection of the temperatures we can achieve as a function of PT. This region is ALICE-3. I think this is the estimate we can get integrated from run 4. So this is extremely interesting. And then I think a few weeks ago, Ralph also mentioned that the moment that this spectrum starts becoming exponential, then that might be an indication that you've hit the pre-equilibrium phase. So I think it could also be a very interesting endeavor to look at how the shape of this evolves when you keep going to higher and higher PT, to see if we can really say that there's a particular temperature where this is pre-equilibrium and when it's at equilibrium. I mean, that's just my personal speculation. I'm sure there needs to be a serious theory to do so regarding these pre-equilibrium studies, but it's certainly something to think about. Now, with the dielectron measurements, we can also continue our searches for chiral symmetry restoration. I mean, this is really one of the long sought after evidence of QGP formation. It's a fundamental feature of high temperature QCD. And essentially what we're looking for in these measurements is evidence of the rho and A1 states within the QGP, the spectral functions, evidence of those mixing and essentially merging, which would be a consequence of these states essentially losing their ability to generate mass in the same way they would do in the dilute environment. So if you have such a mixing mechanism, essentially what you start having is deviations from this sort of exponential behavior in this region. These are the expected deviations for this mixing mechanism, and these are our errors. So we should certainly be able to see any change of shapes of this nature with the current Alice-free proposal in that setup. Now I'll move on to heavy flavor interactions in the QGP. So these amazing point-in resolutions really mean that we can very cleanly identify D0 hadrons. Essentially, I have a plot in the backup where the signal completely dominates over the background. And that really opens the door up for two-particle correlation measurements. They're very difficult if background gets mixed in, but of course very easy if they're clean. And what I have in the middle is a plot with a DD bar correlation, which should come from a CC bar. And the idea is that these will be able to help us probe QGP charm diffusion quite much more directly. So what we do at the moment is we have measurements of charm V2, so to speak. We then compare them with a transport model, which has diffusion as one of the inputs, and that diffusion, and we see what that yields. But there is a proposal that we can use these types of correlations, and essentially, when you start changing the PT, you then might start going from diffusion that comes from collisional interactions to diffusion that comes from radiative interaction. So one can actually also have a handle on the diffusion processes themselves. On the right, I have an estimate of the beauty baryon V2. We have the projections for Alice-free compared to ITS-free and ITS-2. And the idea is we would start really testing the limits or investigating bottom quark diffusion. It's quite, so with the diffusions, you have corresponding relaxation times, which basically tells you how long you need to wait for the thing to couple with the medium. And with charm, this is usually less than the QGP lifetime, but with bottom, it's either the same or perhaps greater. So this would then actually help us explore the limits on this equilibrium processes when you start increasing the mass of the thing that's subject to equilibration and diffusion. We also think we can carry out new tests of lattice QCD in particular for the QGP transition. As many people know that attend the seminar regularly, the measurements of fluctuations of net quantum numbers, these can be used to explore the chiral features of this transition. On the left is some of our estimates just for the higher order proton fluctuations, where the sort of Alice-free estimates are here, and this is what we can measure so far with two predictions, one for the hadron gas resonance and then another prediction that I can't quite remember where that's from. We're also exploring using charm mesons, in particular D mesons, if we can look at event-by-event fluctuations of or what we can learn from event-by-event fluctuations of charm and then the higher order moments and so on and so forth. This is quite interesting, is that there is a big difference between lattice and the hadron gas model. In a certain configuration, one can make this be similar by introducing charm resonances that we haven't yet discovered yet. And we think these sorts of studies will be accessible for the first time, Alice-free. Moving on to multi-charm baryon production. So as many of us know, and certainly for the light flavors, you know, we find the statistical hadronization works extremely well, which means that in this case, we can describe 21 different particles with a model that assumes thermal equilibrium, and just as 2 examples. And I think this is perhaps an interesting example of emergent behavior in QCD, something that you cannot understand from the Lagrangian directly, but just seems to come out when we study the behavior of these systems, that they somehow produce particles statistically. It's a very interesting question to the extent this applies in the charm sector. And I think we can do unique tests with many of these multi-charm baryon states. And also many of these things can only be produced by coalescence. So this looking at the sort of microscopic versus macroscopic contributions or frameworks of hadronization is something we can address in a new way with these multi-charm baryons, because they really should be made by coalescence as far as I can understand. And then we have just a simulation plot of the doubly charged Xi baryon, the DCA with respect to the primary vertex. We can also, I think, we'll go into a new era of exploring hadronic interactions, in particular looking at 2-particle D0 femtocorrelations. One can then see if these can provide any evidence that we can form a D0 anti-D0 molecule, so to speak. This is actually one of the candidates for the tetraquark, the TCC tetraquark that was discovered by LHCb a couple of years ago. And with Alice Free, we also have some simulations that demonstrate that we think the first observation of a charmed nucleus, if it exists, in this case it would be a lambda c coupled with a neutron, would indeed be feasible. Moving on to ultra-peripheral collisions, and I think it's fair to say these have really emerged as a very powerful tool to explore both cold nuclear matter effects and actually much more. I actually have the latest results of the J-side cross-section versus the center of mass energy that was released by the Alice collaboration. Essentially what this does is it looks at. Oh,
you have sorry. 5 minutes remained.
Yes. I'm almost done. So no worries. Yeah, so they've experienced being useful. Essentially, these mirrors the differences in the gluon distributions, and what we find is very strong shadowing effects down to 10 to the minus 5x. With the increased acceptance of Alice Free, we will be able to look at more complicated decays, in particular this excited rho decay that goes into 4 pions. This is more of a question of hadron states, and in particular this type of measurement, we can help resolve one of these long-standing questions, whether this excited state is either 1 state or 2, by looking at the differences between 2 and 4 pi decays. This is something that Starr looked at a few years ago, but I think this question is still quite open. We also have this forward conversion tracker that I mentioned, and it takes advantage of Lorentz boost, which means we can look at photon productions that have an extremely small transverse momentum, only of a few MeV, and I have a couple of performance plots here. And this is quite interesting because when it comes to quantum field theories, you can really test these infrared limits. So the limit of essentially very soft interactions, where I think if I remember in QED, the coupling constant goes to 0, but in QCD, the coupling constant I think may become finite. So testing the limits of quantum field theories again, I think would be an exciting thing. It certainly goes a little bit beyond our typical physics, as does the next slide, which is our what perhaps we can do with beyond standard model searches. So we know recently there was an AMS discovery of the I think of around 10 anti-helium nuclei, and then there's this question: is this too much? Can it come from some mechanism that we don't know about? And dark matter production is perhaps one candidate. One can test this specifically by looking at the beauty baryon decay into an anti-helium free and something else. And here are our limits that we can put on the branching ratio with that this decade. And this is then what we can do with Alice free. We also discovered light by light scattering at the LHC, and there has been a proposal that this might be mediated by a non-standard model particle, the axion, and these are the limits that the Alice can provide. This is the mass, and this is 1 over the coupling of the process. So I've just given you a few physics topics, but I'm sure there is many more that can be explored. So in particular, the fact we have large eta and PT acceptance and excellent PID. So one can look at things like heavy flavored jet correlations or photon heavy flavored jet correlations with very high purity at low PT. And one can start to look at two particle correlations with very large eta gaps, which really should probe the early time dynamics and the fusion of things created in the QGP. We actually, in Alice USA, we actually started to think about more physics topics with Alice Free. And we put a paper on the arXiv that lists those. So you're very welcome to read them. So let me summarize. I think, well, I certainly believe that if we build this detector, it'll open up a new area of discovery, potential, and precision in QCD. Again, I want to remind you at the LHC, it's something that is designed by heavy ion physicists for heavy ion physics. And with that design, I think it has an extremely versatile setup that will allow for a very broad physics program within and beyond QCD. And of course, it continues our hugely successful endeavors of making the world's most powerful microscopes. And I've got perhaps a slight provocative plot here where one compares the Alice data rates and pointing resolutions with the detectors at RHIC and others at the LHC. And I think one can see that we're going to be extremely competitive for future measurements. So I will finish and thank everybody for their attention.
Okay, so thank Andoli very much for your very nice and comprehensive presentation of the LHC. So now it's time for questions, comments, and discussion. Yeah, let's come to our first question from whom, or raise your hand.
Krishna has his hand raised, and Nu also.
Yeah, please.
Nu, why don't you go first? It's probably better for an experimentalist to go first.
Okay, thank you. Yeah, thank you for the nice talk. Can you go back to slide 20, I believe around 25, about chiral symmetry? Could you say it again? What is the idea? How to address issue of chiral symmetry restore? Yeah, this is the plot, especially I think the lower plot. I tried to figure out a few times, still don't really get it myself. So yeah, thank you.
No problem, Nu. Let me try.
Can you full screen? So
of course,
very tiny for me. Yeah. Okay. Yes.
So
thank you.
In vacuum, you know, the A1 resonance has a higher mass than the Rho resonance, and they have different spectral functions. And the idea, if you get chemical symmetry restoration, that these spectral functions start to look the same, so they can't be distinguished anymore. Now, both these particles, when they decay, emit electrons, and if this mixing mechanism occurs, Nu, then that would have an impact on the shape of the invariant mass distribution. And to put it simply, what we have is two scenarios with mixing, which is the black, and without mixing. And then with the mixing, and I think maybe I said it wrong when I gave the presentation, the spectrum shifts up, and without it shifts down. So these two guys, this is essentially the difference in the effect with and without mixing, and this is our expected uncertainties.
Anthony, I think part of the issue is that if I look at the data over cocktail at the bottom, I can't see I only see one black dashed line. Whereas the legend has two different lines. The plot is just not clear. Which one can you just show us with your cursor what curve in the data over cocktail at the bottom is with and without mixing?
I think it's the data divided with mixing. And then one has a reference what this would look like without mixing. So one could just take this theory curve if you like, and if one gets one, you could claim the mixing happenings. But I also agree perhaps this plot could be better presented.
So with mixing is 1 in the bottom plot, and without mixing is the black dashed curve.
Yeah, and then I think there's a vacuum reference as well.
Vacuum reference that's labeled clearly. But still, I don't think in heavy ion collisions we've ever seen the A1, have we? So I think, speaking as a theorist, it's absolutely correct that what you want to look for is the rho and the A1 merging, but I don't know how to do that experimentally. So I'm not sure how is the calculation done, and how does it consistent with the fact that, to my knowledge, no experimentalist has seen the A1 in heavy ion collisions.
No, we A1 because decay to 3 particles.
Exactly.
Including pi and 0.
But what you're looking at
here, I guess here has nothing to do with A1.
No. This is he's saying
A1.
this is right. No, he's saying this is rho A1 mixing. So that's what I'm asking is how does rho A1 mixing affect this plot?
Right, that's right. Yeah, that's part of my puzzle. Yeah.
It's a good question. I can't remember off the top of my head, to be honest, what A1 features we've seen and what we have seen. I know it's quite a broad state, so that means it's very difficult to reconstruct experimentally, because it gets it's distributed over a very large invariant mass. We do have some femto studies that look at the possibility. This was done by Tom Humanik at Ohio State, so I have to look at his studies in terms of what we know about the A1 right at this moment.
Yeah, it's broad and it decays to 3 pions. And I mean, we theorists have been saying forever that what you should look for is the rho and the A1 merging. But we theorists, I don't think have told you how to do that. So I'm curious which theorists made these black solid and dashed curves and how they were done.
I think this is this old observation that in a medium that contains thermal pions, you see pi A1 scattering in the rho spectral function. And that's an ancient observation that goes back to like Kapusta and Shuriak in the early 90s or something like that. I think that's what the calculation is. It's an update on this old Kapusta-Shuriak thing.
Okay. I had a different question when it's my turn.
I'm done. Yes. Thank you, Krishna.
So Anthony, completely different question. So to me, as a theorist, of course, I'm not the best person to look at new detectors and ask questions, but the thing that even I notice is that there's no hadronic calorimeter. You mentioned several times, you mentioned things like heavy flavor jet correlations. If to do jet physics, it's advantageous to have a hadronic calorimeter. I note that you have an absorber. Has anyone considered, instead of an absorber to putting where you have an absorber, to use an HCal as your absorber? In other words,
yes.
How seriously the reason you don't have an HCal, is there some serious obstacle that prevents you? How seriously has it been considered?
I don't know the reason it's not in there, but I do know there has been a group of people thinking about putting one in, Krishna, and that's probably the best answer I can give you to enhance the jet capabilities, the jet type measurements at high measurements. So that's probably as much as I know, and it's probably not the best answer, but it's certainly been considered. I mean, I guess one would have to, of course, ask what sort of jet program you would get with this compared to using other ways to
right. You would have to ask what jet program you get compared to CMS and Atlas in Run 5. But that's not the question that I was going to ask you. I think that given that you were talking about correlations between heavy flavor, which this detector is amazing at, and jets, I would think that if you wanted to do heavy flavor jet correlations, you would want to have good jet capabilities, maybe not compete with CMS and Atlas, but have good jet capabilities. And it would seem that you could do better with an HCal. And so if there's some like obstacle in the sense of, if there's a technical obstacle, like there's no real estate in which to put it, then that's one thing. But I see an absorber there, and I wonder whether absorber could be HCal instead.
HCal instead, yeah. It's a good question, Christian. As I say, I certainly know there's been groups interested, and I will talk to my friends in Alice next time I go to an Alice meeting and see what the status is there. I'm sorry I can't give you a better answer, but there's certainly been some interest.
Well, Andrea has his hand raised. Maybe he wants to ask another question, or maybe he wants to answer that.
Yeah,
yeah. Andrea is he's.
Yes, hello everyone. Maybe I can say a couple of words on this. So in this, there is no, if I'm allowed that way.
Of course.
There is no.
Sure. Yeah, please.
There is no principal reason why there is no, one cannot put an HCal instead of the absorber. So the main consideration is that it would still be very hard to have competitive high energy jet measurements with Atlas and CMS. So the focus here would be on moderate and low momentum jets. And
of course, because you don't have the magnetic field.
And yeah, the magnetic field we would have, because the baseline is a 2 Tesla magnet, which gives excellent PT resolution, in particular in the low PT region up to 10-20 GeV. And then the idea would be to use charged tracks to reconstruct jets, which is something that we are already extensively doing in Alice, and we see that it works very well for moderate energy jets. So that is the current baseline, but there is no principal obstacle in considering an hadronic calorimeter outside the magnet. And of course, we are also open to ideas, suggestions from the community with additional motivation for extending,
also,
modifying the scope.
While we have this diagram up, why is it different on the right than on the left? In other words, there's 2 forward directions and they're different. What's the thinking behind that?
You mean
I'm not sure. Yeah, there's an FCT on the left, but not on the right, and there's ECAL on the right, but not on the left.
Well, FCT would be specialized for this few MeV photon measurements to test the low theorem. And that you don't need to do on both sides. That is a measurement that we would do in PP collisions, therefore a symmetric system, and therefore you need the detector only on one side.
And then why ECAL on one side and not the other?
That I have to check. I think it is for practical reasons, because on the other side, one has to bring out all the services of the barrel detectors that are in the central part. They have to come out somewhere, and yeah, that is where they would come out. You see, there is a gap between the RHIC on the left, and the magnet, and there one would route all the services.
Next question from Lou, please.
Yeah, since we are on this plot, maybe Anthony, you already said, for mid rapidity, let's say ±1 unit, what is the PT coverage? How low this detect? Because really low PT is still an open issue for many physics measurements.
Yeah, it depends on the particle, I would say.
Now, how about the pions, for example, charged pions?
Yeah, I think this is probably the best the best plot to answer your question. So of course, the heavier the particles, the higher their energy loss. So then at some point, the energy loss just prevents them coming in, not the magnetic field. But with the fast pions, it looks like we can go to about 50 MeV.
Oh, okay. Okay.
Yeah, but then when it comes to charged kaons, as I say, you're not limited by the field, but just I think the energy loss, and then it would be 150 for kaons and about 200 for protons. No, of course, because electrons are light, they can come from even lower than that.
Okay, thank you. Yeah.
Thank you, Krishna and Thomas and Anna here for your questions and discussion and comments. There are more questions from our other colleagues. Yeah, maybe I have a please, no.
No, I don't see any hands. That's what I'm saying. Yeah.
Okay, maybe I have a question. About how is the 4-car being considered in LHC? If the 4-car, so now the 4-car actually more or less for run 4.
Run 4.
4-car we are included in the LHC plan. How might it physically different from the run 4, or is there any more or more new physics?
Yeah, I perhaps let Andrea comment afterwards, but there is a proposal to put it, I think, in this side. And obviously, at the moment, we're just trying to make sure the focal happens for run 4, which includes getting all the funding that we need. But yes, I know there is a proposal for Alice Free, and I can't quite remember if they're able to put it a little bit more forward. I mean, at some point when you get too close to the beam, it doesn't work so much. But Andrea, I mean, have you been keeping track of the potential of putting the focal in Alice Free?
Nothing to add with respect to what you said. You said correctly. Yeah. This is being looked at. It is not straightforward to integrate the detector, and one important aspect is also to consider which extension of the focal physics program one could achieve by running it with Alice 3, with respect to what we will have done during round 4 of the LHC.
Yeah. Thank you. Yeah. So more questions? We have time. We have another 15 minutes. So, yes, please, Derek. Yeah, please.
I mean, got mentioned a little bit. I mean, I'm interested in these very soft pions and capabilities of this detector to measure soft pions and both charged and uncharged. And I mean, I don't see any hope for uncharged, but I wondered, and maybe you said it, and I know there was a small discussion, but if I could ask just a little bit more about that. So initially they were talking about like measuring down to 10 MeV, right? Yeah. Is that still the case, or has that been changed, or?
I can't quite remember the plots, but this simulation is done at 2 Tesla, Derek, and then I think if we went down to 0.5 Tesla, that would be even more possible. But what do we have? 10 MeV. That would be this. Now, I don't know if we could ever get the pions down to 10 MeV. We can certainly get these photons at forward rapidity down to those values.
I mean, so, but maybe 50 MeV. I mean, so
yeah.
Of course, so you say if you had a small field run, then you could go to lower momentum, right? I mean,
Yeah.
I don't know. I mean, 10 is an overstretch. I mean, then, you know, the pions are really non-relativistic. At
Yeah.
50, I would like to see at least nice measurements at 50, right?
So I presume you're interested in this huge deviation we get in the spectrum in pions that nobody quite understands.
Yeah,
when
I mean,
blast wave
and also, yeah.
Yeah. Yeah, I think, and yeah, I think we have this plot in the smaller build configuration, Derek, in the letter of intent. So I can try and find it for you.
I mean, I just think that there's interesting physics there related, much more deeply related to chiral symmetry breaking than the rho A1 mixing. And so it would be a shame to let it go.
Yeah, I agree.
Okay. So more questions? We still have time.
Sometimes we run out of questions. Then we can go and enjoy the nice weather outside.
Yeah. Okay.
It was a very nice talk.
Xiaozi. Yeah, please. Oh, sorry.
Yeah. Okay. Thank you. So thank you for the nice talk. So because we have time, I just have a quick question. So as you know, quarkonium was proposed as the very good like the thermometer of the QGP.
Yeah.
So 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 I'm not sure if in future run LHC. So of course we will have the very precise measurement of the quarkonium. So I'm not sure if this can tell us something about the temperature of the QGP, or at least as a complementary to the like the dielectric measurements.
Yeah, that's certainly mentioned in the letter of intent, of course. Quark a critical signature, and I list some of the regarding these detector choices. It's sort of listed, you know, what do we need to do to measure the size, psi-C1 and so on and so forth. But of course, measuring as many quarkonia states as one can is yeah, extremely interesting regarding melting and so on and so forth. And there's definitely some considerations in the letter of intent in that direction.
Okay. Ooh.
Yes, maybe on this, if I may add, exactly the measurement of the Chi-C, of the Chi-C, sorry, into J-psi plus gamma is a measurement that has not been carried out before, and it will probably remain out of reach until then in heavy ion collisions. And this is something that we want to try to achieve with this detector, using indeed the photon reconstruction in the electromagnetic calorimeter and then the J-psi to the muons. And that, of course, will bring new information, because it will tell us how much feed down we have to the J-psi from this state.
Okay. So more questions or comments and so on? So if no more, maybe, so let's thank our speaker, Anthony, again, and thank all participants for your participation and discussion and comments and explanation and so on. So thanks all colleagues.